Welcome back to the Artificial Intelligence to Very Intelligence Launchpad Masterclass. So far, your Python has lived on your own machine. Today, we break out of that box, reaching across the internet to fetch real web data and engineering it into a clean, structured pipeline you can actually analyze. Let's build it. You have already mastered the foundations of Python logic. By using local libraries like random and string, you successfully generated structural outputs, like an 8-character secure password, entirely within your own machine. These foundational skills are a starting point, but they operate in a closed, isolated environment. To perform modern web-scale data analysis, your code must reach out into the world and retrieve external data. This flowchart illustrates the concept of interprocess communication. On the far left, we have your local machine, the web UI or client. To bridge the gap to the external world, your code must send a request across the internet over the HTTP protocol to reach a remote backend server shown on the right. Notice the barrier symbol appearing on this connection line. The information sent from the server arrives as a sequence of text characters. Python treats this as a string of symbols rather than numerical objects, meaning you cannot run mathematical operators or conditionals on the raw payload until it is converted into a compatible type. To analyze real-world information, developers architect a strict deterministic pipeline. This pipeline must securely fetch the external payload, translate it into a readable format, and finally structure it into a grid ready for mathematical manipulation. Professional programming is the engineering practice of safely transporting untyped web data and transforming it into structured computational matrices. We begin at the very first step of our pipeline, connecting to external endpoints. Python achieves this using the HTTP protocol managed efficiently through the requests library. When client applications talk to servers, they rely on JSON JavaScript object notation. JSON is the industry standard payload format for interprocess communication because of its parsing speed and a universal key value structure. To retrieve this JSON data, we use the GET request. This is the default HTTP method used when a client asks a server for specific information. This diagram breaks down a GET request URL into two distinct parts for passing parameters. First, we have path parameters separated by slashes, which act as a direct structural path to a specific resource. Second, we have query parameters appended after a question mark, which act as specific filters applied to the data you are requesting. The GET method carries a specific vulnerability. All parameters you pass, whether path or query, are fully exposed directly in the URL address bar for anyone on the network to read. When you need to transmit complex or sensitive payloads, like authentication details or user IDs, you must switch your transport method to a POST request. This split-screen comparison reveals the mechanical difference. On the left, the GET request exposes its data openly in the URL. On the right, the POST request encapsulates your sensitive information inside a hidden JSON payload. A robust API call requires 4 specific structural components. You need the exact URL, the data payload, a timeout limit to prevent indefinite freezing, and the headers. Headers contain metadata, including the content type, which explicitly tells the receiving server to expect a JSON-formatted payload. Once you send this request, the server returns a status code. A 200 series code means success. A 400 series code indicates a client error, like a bad URL. A 500 series code means you reached the server, but an internal exception occurred on their hardware. Choosing between GET and POST is an architectural decision, dictating the security of the transport layer. Once you successfully receive a 200 series response, you move to the second node in our pipeline architecture, processing the returned JSON payload. Here we hit our mathematical barrier. Python engines cannot perform numerical operations or conditional checks on a payload formatted as a JSON string. Look at this animation where the JSON library translates network-friendly strings into Python-friendly dictionaries. This translation layer acts as the mandatory bridge mapping internet text into usable local data structures. Following this two-way directional flow for in-memory strings, we use json.loads to load a string into a dictionary, and json.dumps to convert that dictionary back into a string for transport. Notice the separate flow appearing here for physical files. When reading or writing data directly to a hard drive rather than computer memory, we use json.load and json.dump. Without this translation layer, fetched web data remains completely inert and isolated from Python's processing power. We arrive at the third pipeline node. We now upgrade our raw Python dictionary into a computationally optimized data structure using the Pandas library. Pandas offers two primary storage structures. The series is a one-dimensional list paired with an index. The data frame is a two-dimensional tabular grid, complete with rows and columns. Watch as this chaotic swarm of disorganized data points instantly snaps into a rigid 2D grid. Analysts ingest massive data sets from massive CSV files or SQL databases directly into a Pandas data frame using a single line of code like read CSV. Once the data populates the grid, you execute Exploratory Data Analysis or EDA. This is the mandatory first step to survey the newly ingested matrix before applying logic. You establish the preview boundaries using head to isolate the first 5 rows and tail to view the final 5 rows. Next, you apply structural summary commands. Calling shape returns the exact dimensions of your grid, while info reveals column data types and identifies any missing values. The describe command provides a statistical baseline, calculating the mean, median, standard deviation, minimum and maximum values for every numerical column in your dataset. To categorize textual or categorical data, you use value counts and unique to locate distinct occurrences and measure exact category frequencies. The Pandas DataFrame transforms a chaotic data dump into an interrogable, predictable environment. With the matrix structured, you enter the next phase of analysis, isolating specific rows and columns to filter out noise. Pandas provides two commands for row extraction, iloc and loc. They obey entirely different structural rules. Look at this 2D data grid. iloc or index location operates purely on integer index locations. It follows standard Python logic where a range stops at n-1. If you query a range of 0 to 5, it highlights rows 0, 1, 2, 3, and 4. Leaving row 5 unselected. When we switch to loc, the highlight expands. LOC utilizes textual labels and includes the upper bound of the requested range, selecting rows 0 through 5 inclusive. To drill down further, you apply multiple filtering conditions by placing core Python logical operators like AND or OR directly inside the data frame brackets. This brings us to feature engineering. If you write a mathematical operation that subtracts a cost column from a sales column, Pandas automatically calculates that difference across every single row, generating a new profit column to hold the results. Pandas eliminates the need for manual row-by-row looping. It grants developers the ability to mathematically manipulate millions of records simultaneously. Real-world pipelines encounter external datasets that are inherently messy and filled with incomplete fields. When Pandas encounters missing, corrupt, or empty values, it explicitly tags them as NaN, not a number. This data frame grid demonstrates the brute force remediation approach. Calling dropna will delete any row containing a null value, causing the data set to physically shrink. You use this only on massive data sets, where slight data loss is acceptable. Watch as those deleted rows return to the grid. This is the substitution method. By calling fillna, we overwrite missing gaps with a designated mathematical standard, such as the numerical average of that specific column. Now look at the overlaid line graph. For advanced time series remediation, Interpolate calculates overarching trends based on surrounding data points to guess the gap. Alternatively, bfill safely copies the next known valid data point backward. Decisions regarding NaN values dictate data integrity and directly influence every downstream statistical analysis. This completed flowchart maps our exact end-to-end Python data pipeline. A web client initiates an HTTP request, translates the JSON, and feeds it into a Pandas DataFrame for final mathematical structuring. But this pristine pipeline exists on a volatile internet. Server connections drop, timeouts occur, and endpoints fail. The professional standard dictates that you wrap all external API calls in try-except blocks. This catches network connection errors before they trigger a complete program crash. You must also monitor your external dependencies. When an API URL is retired, like the CoinDesk endpoint, you must manually route your pipeline to an alternative, like CoinGecko, to maintain the data flow. Consulting external documentation, referencing PyPI, or keeping cheat sheets open is a standard operational procedure in the modern developer workflow. In the next phase of the curriculum, we will take this clean, validated data frame and feed it into NumPy for high-performance array computing and Matplotlib for visual storytelling. Mastering this exact translation. Pipeline allows you to engineer resilient real-world data systems. And there's your complete end-to-end pipeline, an HTTP request, translated JSON, structured into a clean Pandas data frame. Next time, we feed that validated data into NumPy for high-performance array computing and Matplotlib for visual storytelling. That's where your numbers come to life. If this helped, subscribe, and I'll see you in the next one.